Hello, everyone. Welcome to 11th hour. Today, we are going to look at a concept called reactance. We know what a resistance is. A resistance is an element which opposes the flow of current. A reactance does the very same thing, but it is the resistance offered by elements like capacitors or inductors. So, the resistance offered by a capacitance is called a capacitive reactance. I'll denote it as XC, and the resistance offered by the inductor is called inductive reactance. A circuit could have all the three components, right? It could have a resistor, it could have an inductor, and it could have a capacitor. In that case, the entire circuit is not said to have a resistance now, it is said to have something called impedance, where impedance is a combination of all the three. So let us dive into the topic a little more and understand how the reactances are represented in the expression for impedance. Suppose I have a circuit, say this very circuit, let me remove this and complete this circuit over here with a AC voltage source connected to the R, L, and C. Say all the three are connected in series. This is given as V, where V is a sinusoidal voltage source given by Vm sine of 2 pi ft, where f is the frequency of this AC source. Now, there would be a current circulating through this circuit. So, say that is I. When I flows through the resistance, then what would the value of that I be? Right? So, it is just going to be V by R. Or when I replace V with the actual expression, it will be sine 2 pi ft divided by R. So here, if we see the expression for the magnitude of current is Vm by R. Let me call it as IR because this is the current which is flowing through the resistor. So IR sine of 2 pi ft. This is the current which is flowing through the resistor. If we see, both input voltage and the current through the resistor are having sign components in them. They are in phase with each other. There is no phase difference between the two. Now, let us look at the current when it flows into the inductor. So, we know that we can obtain the value of the voltage across the inductor. So, that could be given as VL is equal to L di by dt. Suppose we want to obtain the current through the inductor, then we can reframe this equation and say IL is going to be equal to 1 by L integral V dt. So the overall voltage over here is V. So when I replace it with the expression, sinusoidal expression, what I would get here is 1 by L integral Vm sine of 2 pi ft dt. And on integration, I will get 1 by 2 pi f into L into this Vm, because all of these are constant terms, minus of cos 2 pi ft. So this is the expression for the current through the inductor. Let us now observe the phase of this, right? Here we see that this is a cosine term, a minus cos term. So I can actually rewrite this as IL is equal to Vm by 2 pi fl into sine of 2 pi ft minus 90 degrees, right? Because the cos can be written as sine of theta minus 90. Okay. So this is how I can obtain the expression for the inductive current. Let us now move on to the expression for the uh, capacitive current in this circuit. So looking at the current through the capacitor, right? So I can say IC can be written as C into rate of change of voltage, C dV by dt. We know that the expression for V is Vm sine of 2 pi f into t. So on differentiating it, what do we get? We get d by dt Vm sine 2 pi ft and CVm into 2 pi f All this comes out, and what remains is going to be cos 2 pi ft. So I can write it as Vm into 2 pi f into c into sine of 2 pi ft plus 90. So this is the expression for my current through the capacitor. So I can call this entire thing as, say, capital IC sine of 2 pi ft plus 90, and the expression for IL, what we had obtained was Vm by 2 pi fl sine of 2 pi ft minus 90. This is what we had obtained, where I can replace this expression with capital IL. Now let us observe the three current terms very closely. So IR was nothing but Vm by R sine of 2 pi ft. This is in phase with the supply or the input voltage. The current through the capacitor is 90 degrees leading the phase of the input voltage, and the current through the inductor is lagging by 90 degrees from the input voltage. So if I am able to draw a phasor diagram for this, if this is going to be my 0, so current IR will be like this in phase with my voltage. Then this is going to be the IC, current through the capacitor, and this is going to be IL, current through the inductor, because it is 2 pi ft minus 90 IL, and this is 2 pi ft plus 90, that is IC. So current in a capacitor leads the voltage, current in an inductor lags the voltage, both by 90 degrees. Having understood this, let us now also look at the expression for XL, XC, and of course R, right? So here we know that the resistance here is resistance. And let's look at the expression for the capacitive reactance. So we know that IC is Vm into 2 pi Fc. So that is the capital IC is given as Vm into 2 pi Fc, and we know Vm by I is equal to Xc. So I can say Xc is equal to Vm divided by Ic. So when I cross multiply, what do I get Xc as? It is given as 1 by 2 pi f into c. So Xc turns out to be 1 by 2 pi Fc. On the other hand, if I look at the expression for IL over here, right? So IL, now Vm by IL turns out to be nothing but 2 pi f into L. So Vm by 2 pi fl is IL, and when we cross multiply, we'll get this. So this is nothing but XL. So let's summarize the expressions for XL, XC, and also the phasor relationship for the currents in the reactive components in a circuit. So summarizing, we see that the current through the resistance is going to be in phase with the input. So that is Vm by R sine of 2 pi ft. The current through the capacitance is Vm into 2 pi Fc sine of 2 pi ft plus 90. So it is leading the voltage. Similarly, the inductor, through the inductor, it is going to be Vm by 2 pi Fl sine of 2 pi ft minus 90. So the current is lagging the voltage by 90 degrees. Now let's look at the expression for Xc. So we can rewrite this actually, and we obtain Xc to be 1 by 2 pi Fc, and XL is obtained as 2 pi f into L, because after all Vm by XL is IL, capital IL, and Vm by Xc is equal to IC, and that's how we arrive at these expressions. So what is the expression for the impedance of a circuit? So let's go back to our phasor diagram. So I can say this is XC, this is R, and say this is XL. So we can have two cases over here. When XC is equal to XL, That is one case. The other is when XC is not equal to XL. So when XC is equal to XL, what happens? Both the components cancel out each other because they are in phase opposing each other. So when they are equal in magnitude and they are opposing in direction, they'll cancel out and the circuit becomes purely resistive. So when XC is equal to XL, the impedance is just R. The next case is when they are not equal. So either XC is going to be greater than XL or XL is going to be greater than XC. So that will going to that is going to affect the phasor of the current. Whether the current is going to lead or lag depends on whether the circuit is more capacitive or more inductive. So in either case, I can represent Z as R plus J times of XL. Let me put a kink over here, minus XC, the difference between XL and XC, whichever is greater. Now, why have I represented it as an imaginary quantity? So if I look at this as a complex plane, the x-axis is my real plane and the y-axis is going to be the imaginary plane. So therefore we can represent this as an imaginary quantity. Also, the real losses or the real power which is consumed in a circuit is the one which is taken up to perform useful work. The reactive power is not consumed to perform useful work as such. So therefore, it can also be represented as the imaginary quantity over here. So therefore, we can represent impedance as a complex number where the real part is the resistance and the imaginary part is the reactance. So what would the magnitude be? It would be R square plus XL minus XC the whole square whole root. This holds good when we look at it from this phasor diagram also, because this is XL and this is XC. Suppose I uh, assume that XC was greater than XL. So this is the equivalent reactance. Then the value of impedance, the vector impedance would be like this. So the value of impedance would actually boil down to R square plus XL minus XC the whole square the whole root. So this is how we can relate the impedance to the complex plane. That's all with today's video. So it's a very simple concept about reactance and how we can represent the impedance as a complex number with resistance as the real part and the reactance as the imaginary part. Thanks for watching. Please to subscribe to this channel.